When NASA changed a number in November, they didn't issue a press release, they didn't hold a briefing, they didn't explain their reasoning to the scientific community, they just changed it. And what makes this truly unprecedented is that the change happened just days after a Harvard scientist sent them a detailed report questioning their original model, a report they never publicly acknowledged. Now, before you think this is just another bureaucratic shuffle in the endless universe of space data, let me be clear. This specific change affects how we understand an object that's about to pass through Jupiter's gravitational boundary in March 2026, at a distance so precise it defies statistical expectation. We're talking about 3IATLAS, the interstellar visitor that's been accelerating in ways that don't fit our standard models. The numbers NASA altered directly impact whether that March encounter is a cosmic coincidence or something that requires a very different explanation. Stay with me for the next 15 minutes, because we're going to walk through exactly what NASA changed in their JPL Horizons database, why the timing matters, what a leading astrophysicist discovered that prompted his urgent communication to NASA, and why the Jupiter encounter in March 2026 represents a moment of truth we cannot afford to ignore. This isn't speculation. This is documented, verifiable, and it's happening whether the mainstream conversation catches up or not. Here's what you need to understand right from the start. 3IATLAS isn't behaving like a typical interstellar object. It's showing non-gravitational acceleration, which means something is pushing it beyond the predictable pull of gravity from the Sun and planets. For most comets, we understand this perfectly. It's outgassing frozen material turning to vapor and creating a tiny rocket effect. But 3IATLAS is different. The pattern of its acceleration, the steepness of how that push changes with distance from the Sun, doesn't match what we've observed in thousands of other comets. Scientists have been tracking this carefully, and earlier models reflected that unusual steepness. Then, in November, NASA's Jet Propulsion Laboratory quietly updated their acceleration model for 3IATLAS. They switched from a steep sublimation model, which better matched the observational data, to a much shallower model based on carbon dioxide outgassing. And here's the thing. This wasn't presented as a breakthrough based on new observations. No new data was cited, no paper was published explaining the change. The numbers just shifted in the database, and if you weren't watching closely, you'd never know it happened. Why does this matter to you? Because transparency in science isn't a luxury, it's the foundation. When institutions that hold the observational keys to our universe make changes that affect our understanding of potentially historic objects, we deserve to know why. We deserve to see the reasoning. And when those changes happen in the immediate wake of an independent scientist, raising red flags about an improbable trajectory, the timing alone demands scrutiny. This isn't about mistrusting science, it's about holding scientific institutions to the standards science itself requires: open debate, peer review, and transparent methodology. You don't need a PhD to care about this. You just need to care that the conversation happening about our cosmic neighborhood is honest, complete, and accessible. Dr. Avi Loeb, the former chair of Harvard's astronomy department, noticed something extraordinary about 3IATLAS's trajectory. He calculated that in March 2026, this interstellar object will pass within Jupiter's Hill radius, the gravitational sphere of influence where Jupiter's pull dominates over the Sun's. That alone would be interesting, but here's what elevated it to urgent. The approach distance falls near what's known as a Lagrange point region, a gravitationally balanced zone where objects can maintain stable or semi-stable positions. The probability of an interstellar object randomly approaching Jupiter at precisely this distance from the trajectory 3IATLAS is on is vanishingly small. Loeb sent a detailed report to Dr. Davide Farnocchia at JPL, the lead scientist managing 3IATLAS's orbital data, outlining these findings and raising the question that needed to be asked. Could this object be maneuvering? Days later, NASA's database reflected the model changes. No response to Loeb, no public acknowledgement, just altered numbers that conveniently reduced the projected approach distance to Jupiter and downplayed the significance of the encounter. Now, I want you to hit that like button, because what we're about to unpack together is a story that mainstream outlets aren't telling with the depth it deserves, and your engagement ensures this reaches people who care about transparency, who value independent scientific voices, and who understand that the biggest discoveries often begin with someone asking uncomfortable questions. Drop a comment. Team coincidence or team questions? Should JPL explain model changes publicly? Subscribe if you want to follow this story through to March 2026, because we will be here documenting every development, every observation, and every attempt to either explain or explain away what 3IATLAS represents. This channel exists for people who refuse to accept silence as an answer when the questions matter this much. Let's get into the evidence. To understand why the changes NASA made are significant, you first need to understand what they actually changed and what those parameters mean in plain language. The JPL Horizons system is the authoritative database for tracking celestial objects, asteroids, comets, spacecraft, and yes, interstellar visitors like 3IATLAS. It's where astronomers around the world go to get the most accurate, up-to-date orbital information. These aren't just abstract numbers. They're the predictive models that tell us where an object was, where it is, and where it's going to be. For 3IATLAS, the database included something called non-gravitational acceleration parameters, which account for forces acting on the object beyond gravity. Think of it like adjusting a flight path not just for the pull of Earth's gravity, but also for wind resistance and engine thrust. In the case of comets, that extra push usually comes from outgassing, frozen volatiles turning to gas and creating a jet effect. Before November, the model for 3IATLAS used what scientists call a steep radial dependence. Without drowning you in equations, here's what that means. The acceleration effect was modeled to drop off sharply as the object moved farther from the Sun. This steep profile matched what observers were actually seeing in 3IATLAS's behavior. It indicated that whatever was causing the acceleration was highly sensitive to solar heating, ramping up quickly when close to the Sun and diminishing rapidly with distance. This is characteristic of volatile materials with low sublimation temperatures, materials that transition from solid to gas at relatively modest heating. Water ice, for example, behaves this way under the right conditions. The steep model reflected an object that was responding aggressively to solar radiation in a way that didn't fit the typical carbon dioxide or carbon monoxide outgassing we see in most comets. Then, in November, the model parameters shifted. NASA's JPL updated the database to reflect a much shallower radial dependence. This new model suggested that the acceleration was more evenly distributed across 3IATLAS's trajectory, implying a different composition, specifically a carbon dioxide-dominated outgassing model. Now, carbon dioxide is common in comets, and modelling it isn't inherently problematic. But here's the issue. This change wasn't accompanied by new observational data that justified the shift. There was no announcement saying, "We've refined our analysis based on additional spectroscopy," or "New measurements from Hubble have given us better compositional data." The numbers just changed. And when independent researchers went back to compare the updated model against actual brightness observations and acceleration measurements, the new shallow model fit the data worse than the original steep model. Not better, worse. Let me put this in a way that makes the strangeness clear. Imagine you're tracking a car's fuel efficiency, and your initial model says the car burns fuel rapidly in the first half of the trip and much more slowly in the second half, which matches the actual fuel gauge readings you're seeing. Then someone comes along and changes your model to say the car burns fuel evenly throughout the trip, even though the fuel gauge still shows that rapid early burn. The new model is mathematically cleaner, maybe easier to work with, but it doesn't match reality. That's essentially what happened here. The steep model was messy, unusual, hard to explain with standard comet behavior, but it matched the observations. The shallow model is more conventional, fits the standard comet narrative better, but doesn't align as well with what 3IATLAS is actually doing. Why would NASA make this change? There are charitable explanations. Perhaps they believed the steep model was overinterpreting noisy data. Perhaps they thought the shallow model, while less precise, was more physically plausible, given what we know about cometary composition. Perhaps they were trying to avoid amplifying speculation about 3IATLAS being anything other than a natural object, and the steep, unusual acceleration profile was feeding narratives they wanted to cool down. These are reasonable institutional motivations, and I'm not going to pretend they're impossible. But here's the problem. Science doesn't advance by choosing the most comfortable model. It advances by choosing the model that best fits the data, even when that model is uncomfortable, even when it raises questions we don't yet know how to answer. And the lack of transparency around this decision, the absence of a public rationale, the silence in response to Loeb's inquiry, all of that undermines trust in the process. The technical specifics matter because they reveal intent. The original steep model had parameters that indicated a strong solar dependence, meaning the object's acceleration was tightly correlated with its distance from the Sun in a way that suggested high volatility and rapid outgassing response. The updated shallow model spread that acceleration out, implying a more stable, sustained outgassing over a longer period. This has downstream effects on every prediction derived from that model, including the projected trajectory through Jupiter's system. When you flatten the acceleration curve, you change the velocity profile. When you change the velocity profile, you change where the object is predicted to be at any given time. And when you change those predictions for an object heading toward a gravitationally complex encounter, you're not just tweaking numbers, you're altering the story of what this object might do and what we might learn from watching it. The database changes were subtle enough that casual observers wouldn't notice. The publicly available ephemerids, the tables showing predicted positions, shifted slightly, but unless you were comparing historical snapshots of the data, the change would seem like just another routine update. And that's precisely why it matters. This wasn't a dramatic rewrite that would attract attention. It was a quiet adjustment, the kind that could be justified as standard refinement if anyone asked, but also the kind that could be used to subtly reshape the narrative if no one was paying close enough attention. Loeb was paying attention. A handful of other researchers were paying attention, and now you're paying attention. Because the integrity of our understanding of 3IATLAS depends not on trusting that institutions always get it right, but on ensuring that when they make choices, those choices are visible, justifiable, and open to scrutiny. Here's what we know for certain. The model changed. The timing of that change coincided with Loeb's communication to JPL, and the new model fits the observational data less accurately than the old one. We also know that NASA did not issue any public statement explaining the rationale, did not publish a technical note justifying the update, and did not respond to Loeb's report in any documented way. You can verify all of this yourself. The JPL Horizons database is public. Loeb's writings on this topic are public. The observational studies from Hubble and other sources are public. The pieces are all there, and they don't require conspiracy thinking to see that something about this process feels wrong. It feels like a decision made for reasons other than pure observational accuracy. And in science, that's a red flag we can't afford to ignore. So as we move forward, keep this foundation in mind. The numbers changed, the justification didn't come, and the implications ripple forward to everything we're about to discuss regarding Jupiter, March 2026, and what happens when an interstellar object does something that defies our expectations. That foundation is about to become critical. Avi Loeb is not a fringe figure. He's not a sensationalist chasing clicks or building a career on controversy for its own sake. He's a theoretical astrophysicist with decades of peer-reviewed research, the longest-serving chair of Harvard's astronomy department, former director of the Institute for Theory and Computation at the Harvard-Smithsonian Center for Astrophysics. He's published hundreds of papers, mentored countless students, and contributed to mainstream astrophysical understanding in ways that are widely respected. When he speaks, serious scientists listen, even when they disagree with him. So when Loeb began tracking 3IATLAS and noticed something that didn't fit, this wasn't amateur hour speculation. This was a credentialed expert applying rigorous analysis to publicly available data and arriving at a conclusion that demanded institutional response. Loeb's focus was on the trajectory, specifically the parameters of 3IATLAS's approach to Jupiter. He calculated that in March 2026, the object would pass within the Hill radius of Jupiter, a gravitational boundary that defines where Jupiter's gravity dominates over the Sun's. For any object approaching a massive planet, crossing this threshold is significant because it means the planet becomes the primary gravitational influence. But Loeb noticed something more specific. The projected approach distance placed 3IATLAS near a region associated with Lagrange points, positions in space where the gravitational forces of two large bodies balance in a way that allows smaller objects to maintain relatively stable orbits. These are not random zones, they're mathematically defined, gravitationally special, and they're where we find stable populations of Trojan asteroids in our own solar system. For an interstellar object on a hyperbolic trajectory to pass through one of these regions isn't impossible. But the probability is extraordinarily low, especially given the specific angle and velocity 3IATLAS is travelling. He ran the numbers, checked them, and reached a conclusion that many scientists would hesitate to even voice. If this trajectory was intentional, If something about 3IATLAS's path was not purely the result of natural gravitational dynamics and random outgassing, then the March 2026 encounter could represent a deliberate approach to Jupiter's system. Now, I want to be clear about what Loeb was and wasn't saying. He wasn't claiming definitive proof of artificial origin. He was raising the question that the data compelled, given the improbability of this specific trajectory, and given that 3IATLAS is already exhibiting non-gravitational acceleration that doesn't fit standard models, shouldn't we at least consider the possibility of targeting? Shouldn't we be watching this encounter with every available instrument, prepared for the possibility that we might observe behavior inconsistent with a passive, inert object? That's the essence of good science, following the data wherever it leads, even when it leads somewhere uncomfortable. Loeb formalized these observations and concerns into a detailed report and sent it to Dr. David Farnocchia at NASA's Jet Propulsion Laboratory. Farnocchia is the scientist responsible for managing the orbital tracking and modelling of 3IATLAS in JPL's system. He's the person who would receive reports like this, evaluate them, and if warranted, coordinate with colleagues to refine the models or investigate further. Loeb's communication was professional, data-driven, and framed as a legitimate scientific inquiry. It wasn't accusatory, it wasn't sensational. It was a senior scientist bringing something important to the attention of the institution, with the resources and responsibility to investigate. And then, nothing. No public response. No acknowledgement in JPL's publications or communications about 3IATLAS. No indication that the concerns raised were being taken seriously, or even considered worth addressing. What did happen, however, was that within days of Loeb's report reaching JPL, the database entries for 3IATLAS were updated, with the model changes we discussed earlier. The steep acceleration model was replaced with the shallow carbon dioxide model. The projected trajectory parameters shifted, and critically, these changes had the effect of slightly reducing the calculated significance of the March 2026 Jupiter encounter, making it seem less remarkable, less worthy of intense scrutiny. Now, correlation is not causation, and it's possible this timing is purely coincidental. It's possible JPL had been planning this model revision for unrelated reasons, and the timing just happened to align with Loeb's communication. But if that's the case, why not say so? Why not issue a brief statement explaining that the model was updated based on internal review, and here are the reasons? The silence is what transforms a potentially innocent administrative action into something that looks like a reaction, a defensive move, an attempt to reshape the narrative in response to uncomfortable questions, rather than to engage with those questions directly. Imagine you're a scientist who's dedicated your career to rigorous inquiry. You notice something anomalous, something that doesn't fit established patterns. You take the time to document it carefully, run the analysis, check your work, and then you bring it to the attention of the institutional authority responsible for the data. You're not looking for credit. You're not trying to cause problems. You're doing what scientists are supposed to do, flagging something that needs attention. And instead of a dialogue, instead of "thank you for bringing this to our attention, here's our assessment," you get silence and a database update that contradicts your findings without explanation. How would that feel? How would that affect your trust in the process? And more importantly, how should it affect the public's trust in the process? Loeb didn't stop. He's continued to write about 3IATLAS, continued to raise the questions that need to be raised, continued to advocate for transparency and thorough observation of the March 2026 encounter. He's done interviews, published articles, engaged with both supportive and skeptical audiences. He's taken the professional risk that comes with challenging institutional consensus, knowing that doing so invites criticism, knowing that it's easier to stay quiet and avoid the controversy. But he's also operating from a principle that transcends personal comfort. If we don't ask the hard questions about objects like 3IATLAS, if we let institutional inertia or fear of ridicule dictate what gets investigated and what gets quietly minimized, then we risk missing something profoundly important. We risk being the generation that had the data, had the tools, had the warning signs, and chose not to look because looking was uncomfortable. This timeline matters because it establishes a pattern. It shows that independent scientific inquiry, even when conducted by credentialed experts using rigorous methods, can be met with institutional silence and subtle data revision rather than open engagement. It shows that the mechanisms that should ensure accountability and transparency in science, peer review, public data access, institutional responsiveness, can be bypassed when the stakes involve narratives that institutions would prefer not to amplify. And it shows that March 2026 is not just another date on the astronomical calendar. It's a moment where the questions Loeb has been raising will be tested by observation, where nature itself will provide answers that no database revision can alter, either. 3IATLAS will behave exactly as a natural interstellar comet should, passing through Jupiter's vicinity and continuing on its way, or it will do something else, something that demands we revisit every assumption we've made about it. And when that moment comes, the fact that these questions were raised, documented, and ignored will matter. It will matter to the integrity of the scientific process, and it will matter to how we as a species respond to the possibility that we are not alone in paying attention to the cosmos around us. So keep Loeb's timeline in your mind as we now turn to what makes that March encounter so gravitationally and statistically significant. Jupiter isn't just another planet in our solar system. It's a gravitational colossus, a body so massive that it affects everything within its reach, bending the trajectories of comets, capturing asteroids into stable orbits, and acting as a cosmic gatekeeper that shields the inner solar system from many potential impactors. When we talk about Jupiter's Hill radius, we're talking about the boundary of that influence, the invisible sphere where Jupiter's gravity becomes dominant over the Sun's. This isn't a fixed distance. It depends on the masses involved and the distances between them. But for Jupiter, it extends outward in a region where objects passing through experience a fundamental shift in what's pulling on them most strongly. Cross that threshold and you're in Jupiter's domain, and that's exactly where 3IATLAS is headed in March 2026. Let me explain what the Hill radius actually represents in a way that doesn't require a physics degree. Imagine you're in a vast ocean, and there are two powerful currents. One is the broad, sweeping current of the entire ocean, pulling everything in a general direction. That's like the sun's gravity, the dominant force across the solar system. But then there's a whirlpool, a localized vortex with its own fierce pull. When you get close enough to that whirlpool, the broad ocean current stops being the main thing affecting your motion. The whirlpool takes over. The Hill radius is the boundary of that whirlpool's dominance. Inside it, the whirlpool is in control. For Jupiter, this radius extends outward from the planet, creating a gravitational sphere of influence that's substantial, and any object that enters it experiences dynamics that are no longer dictated primarily by the Sun. Now, why does this matter for 3IATLAS? Because the trajectory calculations, even with the updated model, show that 3IATLAS will pass within this Hill radius during its March 2026 encounter, and not just anywhere within it. The approach distance places the object in proximity to what are known as Lagrange points. These are special positions in a two-body gravitational system, points where the gravitational forces balance in such a way that a small object can maintain a stable or semi-stable position relative to the two larger bodies. There are 5 Lagrange points in any two-body system, and some of them are gravitationally stable, meaning objects placed there can stay there for long periods without drifting away. Others are unstable, but still represent mathematically significant zones where gravitational dynamics are unique. The fact that 3IATLAS's trajectory brings it near one of these regions is, from a purely statistical standpoint, remarkable. Think about the odds for a moment. 3IATLAS originated outside our solar system, travelling through interstellar space on a path determined by the gravitational interactions of whatever stellar neighbourhood it came from. It entered our solar system on a hyperbolic trajectory, meaning it's not bound to the Sun, it's just passing through. For its path to intersect with Jupiter's Hill radius alone is not wildly improbable. Jupiter is massive and its influence is vast. But for that intersection to occur at a specific distance that aligns with Lagrange point dynamics, at a specific angle, at a specific velocity that allows for a close but not catastrophically close encounter, that combination of factors narrows the probability significantly. Loeb calculated these odds and found them to be vanishingly small under the assumption of a purely random natural trajectory, not impossible, but improbable enough that it warrants serious attention. Let's go deeper into what happens during this encounter. As 3IATLAS approaches Jupiter in March 2026, its velocity and trajectory will be influenced by Jupiter's gravity. If the object is purely passive, purely a chunk of ice and rock with no ability to adjust its path, then the encounter will play out according to Newtonian mechanics in a predictable way. Jupiter's gravity will tug on it, potentially altering its trajectory slightly, and then 3IATLAS will continue onward, exiting the solar system with a slightly different velocity and angle than it came in with. This is standard gravitational interaction, the kind we've observed countless times with comets and asteroids. But if 3IATLAS exhibits any behavior during this encounter that deviates from the predictions, if it adjusts its trajectory in a way that can't be explained by Jupiter's gravity alone, if it changes velocity in a manner inconsistent with passive dynamics, if it does anything that suggests active maneuvering, then we have a data point that fundamentally changes the conversation. The March 2026 encounter is also significant because of what it will allow us to observe. When an object passes close to Jupiter, we have multiple spacecraft in the region that can potentially gather data. Juno, NASA's mission currently orbiting Jupiter, has instruments capable of detecting magnetic anomalies, radiation signatures, and other phenomena that could distinguish between a natural object and something else. The European Space Agency's JUICE mission, depending on its position in 2026, might also have observational opportunities. Ground-based telescopes will be watching, and if 3IATLAS is bright enough, space-based observatories like Hubble could provide additional data. This is not a moment that will pass unobserved. The question is whether the observations will be comprehensive, whether the data will be publicly shared in real time, and whether the interpretation of that data will be transparent or subject to the same quiet revisions we've already seen. What makes this encounter a moment of truth is that it removes ambiguity in a way that data models cannot. Right now, we're arguing about parameters, about whether the steep model or the shallow model better fits the observations, about whether the acceleration profile suggests something unusual or just unusual within normal range. But in March 2026, 3IATLAS will either behave as predicted or it won't. If it behaves exactly as the updated shallow model suggests, passing through Jupiter's vicinity on a purely ballistic trajectory with no anomalies, then the skeptics will have a strong case that this has always been a natural object and the concerns were overblown. But if it deviates, if it exhibits course corrections, if its acceleration changes in ways that outgassing cannot explain, if it shows any signs of active navigation, then every assumption we've made about this object will need to be revisited. And the fact that these questions were raised in advance, documented and met with institutional silence rather than institutional preparation, will be part of the historical record. I want you to think about what it would mean if 3IATLAS is navigating. Not in a speculative science fiction way, but in a practical observational way. If an object from outside our solar system is capable of adjusting its trajectory, capable of targeting specific gravitational regions like Jupiter's Hill radius, that implies a level of sophistication that challenges our current understanding of what's possible with interstellar travel. It implies propulsion, guidance, power sources, and purpose. It implies intelligence. And while I'm not here to tell you that's definitively what's happening, because we don't have definitive evidence yet, I am here to tell you that the data we do have doesn't rule it out, and the institutional response to questions about it has been inadequate. That inadequacy is reason enough to watch March 2026 with intense scrutiny, regardless of what you believe the outcome will be. Jupiter's Hill radius is not just a mathematical abstraction, it's a real boundary with real gravitational consequences, and 3IATLAS's trajectory through it is either a cosmic coincidence or a cosmic clue. The fact that NASA revised its model in a way that downplays the significance of this encounter, without public explanation, without responding to legitimate scientific inquiry, suggests that there is discomfort with the questions this trajectory raises, and discomfort is not a reason to stop asking. It's a reason to ask more insistently, more publicly, more transparently. Because if we're about to witness something unprecedented in March 2026, the worst possible outcome would be for it to happen in an environment where the data is controlled, the narrative is managed, and the public is left guessing about what was actually observed. We deserve better than that. Science deserves better than that. And 3IATLAS, whatever it is, deserves to be studied with the intellectual honesty and courage that true scientific inquiry demands. So as we move forward, remember this. The Hill radius encounter is not a minor detail. It's the fulcrum on which this entire story will tip, one way or another. The heart of the scientific disagreement over 3IATLAS is not philosophical, it's empirical. It's about what the observations actually show versus what the models claim. And when you dig into the observational data, particularly from high-quality instruments like the Hubble Space Telescope, a troubling pattern emerges. The updated model that NASA adopted does not fit the data as well as the original model did. This isn't a matter of interpretation or subjective judgment. This is about comparing predicted light curves and acceleration patterns against measured ones and seeing which model produces a closer match. And by that standard, the shallow carbon dioxide model falls short. Let's start with what Hubble observed. When a comet outgasses, it creates a coma, a cloud of gas and dust around the nucleus, and that coma scatters sunlight, making the comet appear brighter. The brightness of that coma and how it changes with distance from the sun tells us a lot about what's sublimating and how much. Hubble observed 3IATLAS at multiple points along its trajectory, capturing detailed brightness measurements that allowed astronomers to construct a light curve, a graph of brightness over time. That light curve revealed something specific. The brightness increased steeply as 3IATLAS approached the sun and decreased steeply as it moved away. This steep dependence on solar distance is exactly what you'd expect if the outgassing was driven by highly volatile material, something that responds aggressively to even modest increases in solar heating and shuts down quickly when heating decreases. The original steep acceleration model was consistent with this observed light curve. It predicted that the non-gravitational acceleration, the push from outgassing, would follow the same steep solar dependence that the brightness data showed. This makes physical sense. If the coma brightness is ramping up steeply, it means a lot of gas is being released steeply. And if a lot of gas is being released, that creates a correspondingly steep acceleration. The two are coupled. You can't have a steep brightness curve driven by outgassing and a shallow acceleration curve from that same outgassing. It's internally inconsistent. But that's exactly what the updated model implies. The shallow carbon dioxide model predicts a more gradual sustained outgassing across a broader range of solar distances, which should produce a correspondingly gradual brightness curve. But that's not what Hubble saw. Hubble saw steep. The data said steep. And the model NASA now uses says shallow. This discrepancy has not gone unnoticed by other researchers. Dr. Marshall Eubanks, a planetary scientist with extensive experience analysing cometary data, examined the brightness observations and independently concluded that the steep model was more consistent with what 3IATLAS was actually doing. His analysis, which has been shared in preprint form and discussed in scientific forums, pointed out that the shallow carbon dioxide model requires assumptions about the outgassing pattern that are not supported by the observational evidence. Specifically, it requires that the outgassing be spread out over a larger fraction of the nuclear surface and sustained over a longer period than the brightness data suggests. In other words, to make the shallow model work, you have to assume things about 3IATLAS's behaviour that contradict what we observe about its brightness. Why would NASA choose a model that fits the data less well? There are a few possible explanations, and none of them are entirely satisfying. One is that they prioritised physical plausibility over observational fit. Carbon dioxide outgassing is well understood, common in comets, and produces a shallow profile in many cases. Water ice, or other more volatile materials that could produce a steep profile, are less common in interstellar objects, or at least less expected. So perhaps the reasoning was that even if the steep model fits the brightness data better, the shallow model is more physically reasonable, given what we think we know about interstellar comets. But here's the problem with that logic. We have exactly one other confirmed interstellar comet to compare to, 2I of Borisov, and it behaved very differently from 3IATLAS. We don't have a robust statistical basis for saying what's normal for interstellar comets. Choosing a model based on what's common in solar system comets when dealing with an object from outside the solar system is scientifically questionable. Another possible explanation is that the steep model was seen as too amenable to non-natural interpretations. If your acceleration doesn't fit the standard cometary profiles, if it's unusually steep and doesn't match the expected sublimation behaviour of known volatiles, that opens the door to questions about whether outgassing is the only thing going on. And if you're an institution like NASA, which has historically been cautious about amplifying speculation regarding artificial objects or extraterrestrial intelligence, adopting a model that closes down those questions might seem like the prudent move. But prudence in public relations is not the same as scientific rigor. If the steep model is more accurate, then choosing the shallow model to avoid uncomfortable questions is a betrayal of the scientific method. It's putting narrative management ahead of truth-seeking. There's also the issue of how sublimation works at different solar distances. Carbon dioxide sublimates at temperatures that are reached farther from the sun than water ice, which means a carbon dioxide-dominated comet can remain active over a broader range of distances. This produces the shallow, sustained outgassing curve that the updated model reflects. But for that to be accurate for 3IATLAS, the object would need to have a composition that's heavily skewed toward carbon dioxide, with relatively little of the more volatile materials that would produce steep behavior. And while we don't have direct spectroscopic confirmation of 3IATLAS's composition, it's too faint and distant for detailed spectroscopy with current instruments. The indirect evidence from brightness behavior suggests that whatever is outgassing is not behaving like typical carbon dioxide. It's behaving more like something that turns on hard and turns off hard, something with a narrow temperature band for sublimation. Let's talk about what this means for the predictive accuracy of the model. When you're tracking an object's trajectory, especially one that's exhibiting non-gravitational forces, the accuracy of your acceleration model directly affects the accuracy of your position predictions. If you're using a model that underestimates or mischaracterizes the acceleration, your predictions of where the object will be at a future date will be off. For 3IATLAS, this matters enormously for the March 2026 Jupiter encounter. If the steep model is more accurate, then the object's velocity and trajectory leading into that encounter are slightly different than what the shallow model predicts. That difference might seem small. But when you're dealing with gravitational encounters, small differences in the initial conditions can lead to significantly different outcomes. A trajectory that brings 3IATLAS just inside Jupiter's Hill radius versus just outside it, or that changes the relative velocity at closest approach, affects what we can observe and what conclusions we can draw. The observational conflicts also extend to the broader question of transparency and model selection. In most scientific fields, when a model is revised, especially a model that affects publicly available predictive data, there's an expectation of documentation. You publish a note explaining why the revision was made, what new data or analysis prompted it, and how the new model compares to the old one in terms of fit to observations. This allows the scientific community to evaluate the revision, to check the work, to raise objections if the revision seems unjustified, but that didn't happen here. The JPL Horizons database was updated, and anyone who wasn't actively comparing snapshots of the data wouldn't even know a change had been made. This opacity is not standard practice. It's not how major revisions to important objects are typically handled. And the fact that it happened in the immediate aftermath of Loeb's communication raises the question of whether the revision was scientifically motivated or strategically motivated. I want to emphasize that questioning a model is not the same as accusing anyone of malfeasance. Scientists make judgment calls all the time about which models to use, and reasonable people can disagree about how to balance observational fit against physical plausibility. But those disagreements should be public. They should be debated. The community should see the reasoning, evaluate the trade-offs, and come to a consensus, or at least a documented disagreement, based on transparent analysis. What we have instead is a silent revision, a model that fits worse, and a set of questions that remain unaddressed. And as we approach March 2026, those unresolved questions become more urgent, because the predictions we're relying on are based on a model that multiple independent scientists believe is inadequate. The broader lesson here is that observational data should be the ultimate arbiter. Models are tools, useful fictions that approximate reality, and when reality says one thing and the model says another, we revise the model, not the data. The brightness curve from Hubble is not up for debate. It's measured, it's documented, it's real. The steep dependence is not an interpretation, it's an observation. And if our model can't accommodate that observation without invoking something unusual, then we need to be willing to consider that maybe something unusual is happening. That doesn't mean jumping to conclusions. It means staying open to what the data is trying to tell us, even when it's uncomfortable, even when it challenges our assumptions. The model problem with 3IATLAS is a microcosm of a larger issue in institutional science, the temptation to smooth over anomalies, to fit difficult data into comfortable frameworks, to avoid the hard questions in favour of the easy answers. And when the stakes are as high as they potentially are with an interstellar visitor exhibiting unexplained behaviour, that temptation is one we cannot afford to indulge. When we talk about non-gravitational acceleration, we're talking about any force acting on an object that isn't gravity. For comets in our solar system, this is almost always outgassing. Frozen volatiles, water, carbon monoxide, carbon dioxide, methane, absorb solar radiation, heat up, and transition directly from solid to gas. That gas escapes from the comet's surface, and because it's leaving in specific directions based on where the sun is and where the volatile deposits are, it creates a rocket effect. The comet gets pushed, gently but measurably, in a direction that's not purely determined by the gravitational pull of the sun and planets. This is well understood, well documented, and it's why we have to include non-gravitational parameters in our models for cometary trajectories. Without accounting for outgassing, our predictions of where a comet will be can be off by significant margins. 3IATLAS is exhibiting non-gravitational acceleration. That much is not in dispute. The question is what's causing it, and whether the cause fits within our existing understanding of cometary behaviour or requires us to consider alternatives. The steep acceleration profile we discussed earlier is one clue that something about 3IATLAS's outgassing is unusual. But let's go deeper into what alternatives might exist if outgassing alone isn't sufficient to explain the observations. This is where the conversation becomes uncomfortable for many in the mainstream scientific community. Because once you start questioning whether a natural explanation is adequate, you open the door to considering artificial explanations, and the mere act of considering that possibility is often treated as scientifically heretical, as if asking the question is somehow less rigorous than refusing to ask it. Avi Loeb has framed this in terms of two categories, natural and technological. The natural category includes everything we understand about cometary outgassing, ice sublimation, dust ejection, and other passive physical processes that can produce non-gravitational forces. The technological category includes anything that requires active propulsion, guidance, or energy expenditure beyond what passive physical processes provide. Now, before anyone dismisses this framework as speculative, consider that it's actually the most scientifically neutral way to approach an anomaly. You start with natural explanations, because they're statistically more likely and require fewer assumptions. But if the natural explanations fail to fit the data, you don't stop there. You consider what other categories of explanation exist, and you evaluate them based on the evidence. That's not speculation. That's comprehensive analysis. So let's evaluate the natural explanations honestly. The steep outgassing model, which better fits the brightness data, suggests that 3IATLAS is sublimating something highly volatile, something that responds sharply to solar heating. Water ice is one candidate, but water ice alone doesn't typically produce the kind of steep profile we're seeing unless there are specific surface conditions, high albedo areas, concentrated deposits, rapid rotation that exposes fresh ice, that amplify the effect. Even then, the steepness is unusual. Carbon monoxide is another candidate, more volatile than water, but less common in the concentrations that would be needed to explain the observed brightness. Methane, ammonia, and other supervolatiles are possible, but again, we're reaching for less common compositions to explain what we're seeing, and none of these explanations fully account for why 3IATLAS's acceleration profile is steeper than the vast majority of comets we've studied. There's also the issue of rotation and surface heterogeneity. If 3IATLAS is tumbling or rotating in a way that exposes different surface areas to the Sun at different times, that could create complex outgassing patterns that mimic unusual acceleration. But this introduces additional unknowns. We don't have detailed rotational data for 3IATLAS, and modelling complex rotation-driven outgassing requires assumptions that are difficult to verify. It's possible, but it's also adding layers of complexity to explain something that might have a simpler, though more radical explanation. And in science, while we value simplicity, we also have to be careful not to multiply assumptions just to avoid an uncomfortable conclusion. Here's where we need to talk about the technological possibility, not as a conclusion, but as a hypothesis that deserves evaluation. If 3IATLAS is not purely a passive object, if there's some element of active propulsion or manoeuvring, what would that look like observationally? It would produce non-gravitational acceleration that doesn't correlate neatly with solar distance in the way outgassing does. It could produce changes in trajectory that are directionally specific, not just radial outward from the Sun as sublimation typically causes. It might show acceleration at solar distances where natural outgassing would be minimal or absent. And critically, if the object were maneuvering to adjust its trajectory for a specific purpose, like targeting a particular region of Jupiter's gravitational influence, the acceleration pattern would be whatever was necessary to achieve that trajectory, not constrained by the physics of ice sublimation. Now, I am not sitting here telling you that 3IATLAS is definitively an artificial object. I am telling you that the data we have does not conclusively rule it out, and the institutional response to questions about it has been to adopt a model that downplays the anomalies rather than to investigate them more rigorously. That is a problem. Because if there's even a small probability that an interstellar object is exhibiting active propulsion, the implications are so profound that the question deserves exhaustive investigation, not quiet dismissal. We are talking about the possibility of technology from another stellar system, traversing interstellar space, entering our solar system, and potentially interacting with our planetary neighbourhood in ways that demonstrate intention. If that possibility is real, even at a low probability, it is the most important scientific question of our era. Let's consider what propulsion technologies might be feasible for an interstellar object. Solar sails, which use radiation pressure from sunlight to accelerate, could in principle produce non-gravitational acceleration, but the acceleration profile wouldn't match what we see with 3IATLAS. Solar sails produce acceleration that decreases with distance from the Sun, but in a very specific way that depends on the sail's area and reflectivity. Ion drives, which eject charged particles to produce thrust, could create almost any acceleration profile depending on how they're operated, but they'd require an onboard power source and fuel. Nuclear propulsion, either fission or fusion-based, could provide sustained thrust over long periods. Any of these would produce observational signatures, light signatures, thermal signatures, perhaps even detectable radiation that we could look for if we knew to look. But if we've already decided the answer is natural comet, we're not looking for those signatures. The statistical argument is also worth considering seriously. Loeb has calculated the probability that an interstellar object arriving on a random trajectory would pass within Jupiter's Hill radius at the specific distance and angle that 3IATLAS is predicted to. The odds are very low, not impossible, but low enough that if you're a betting person, you wouldn't bet on coincidence. And when you combine that statistical improbability with the observational anomalies, the steep acceleration, the poor fit of the revised model, the unusual brightness curve, you start to accumulate a set of coincidences that strains the natural explanation. Again, this doesn't prove anything, but it shifts the burden. It makes the question, could this be artificial? Not a fringe speculation, but a reasonable hypothesis that deserves investigation proportional to its potential significance. There's a philosophical point here that's often missed in debates about anomalous objects. The demand for extraordinary evidence before considering extraordinary explanations is often misapplied. Yes, extraordinary claims require extraordinary evidence to be accepted as true, but they don't require extraordinary evidence to be investigated. Investigation comes first. You follow the anomalies, you gather more data, you design observations that could distinguish between competing hypotheses, and then, based on what you find, you reach conclusions. What we're seeing with 3IATLAS is a short-circuiting of that process. The institutional response has been to revise the model to make the anomaly less anomalous, rather than to intensify observation and investigation of the anomaly. That's backwards. That's not how you discover new things. That's how you avoid discovering new things. The March 2026 encounter is, in many ways, the test we need. If 3IATLAS behaves exactly as a passive natural object should, the technological hypothesis becomes much less plausible. But if it exhibits any behavior that suggests active maneuvering, course corrections, velocity changes that can't be explained by Jupiter's gravity, any deviation from the predicted passive trajectory, then the technological hypothesis gains significant credibility. And the conversation shifts from "is this possible?" to "how do we confirm or rule out this possibility definitively?" And that's the conversation we should be preparing for, not avoiding. Because if we wait until the encounter happens and are unprepared, if we're not watching with the right instruments, not looking for the right signatures, not ready to interpret what we see with intellectual honesty, then we may miss the most important observation in human history. That is not hyperbole. That is a sober assessment of what's at stake. So what's pushing 3IATLAS? Maybe it's an unusually volatile comet with a composition and structure that creates steep outgassing in a way we haven't seen before. Maybe it's a fragment of a destroyed planet or moon with surface properties that amplify sublimation effects. Or maybe it's something that's accelerating under its own power, for its own reasons, and our models don't fit because they're trying to describe something our models were never designed to describe. We don't know yet, but we will know more in March 2026, and how we approach that moment, with open minds and rigorous observation, or with predetermined conclusions and selective attention, will define whether we're doing science or just performing it. This story is about more than one interstellar object and one database change. It's about how science is conducted at the institutional level, how transparency and accountability function when the stakes are high, and what happens when the process that's supposed to protect us from error instead protects institutions from discomfort. Science, at its core, is a method for discovering truth through observation, experimentation, and open debate. It's adversarial by design. Your hypothesis is only as strong as its ability to withstand scrutiny from peers who are actively trying to find its flaws. That adversarial process is what makes science reliable. But it only works if the process is transparent, if data is accessible, if changes to models and methodologies are documented and justifiable, and if institutions respond to legitimate questions rather than retreating into silence. What we've seen with 3IATLAS is a failure of that process at multiple points. A model was changed without public explanation. A credentialed scientist raised legitimate concerns and received no documented response. The new model fits the observational data less well than the old model. But that trade-off was never openly debated. And now, as we approach a potentially historic encounter, the foundation of our predictive understanding of this object is built on a model that multiple independent researchers question. This is not how science is supposed to work. And the fact that it's happening with an object as significant as an interstellar visitor exhibiting anomalous behavior makes the failure not just procedural, but potentially consequential. Let's talk about what transparency in science actually means. It means that when you make a decision that affects publicly available data, you document that decision. You explain your reasoning, you cite the observations or analyses that led you to conclude the change was necessary. You invite critique, you engage with objections. If someone credible says, "I disagree with this change and here's why," you don't ignore them. You respond. You either defend your decision with evidence, or you acknowledge that the objection has merit and revisit your reasoning. This isn't burdensome, this is basic scientific practice, and yet it didn't happen here. The change was made, the silence was maintained, and the scientific community was left to speculate about why. There's a broader cultural issue within institutional science that this episode exposes. There is a fear of being wrong in public, a fear of amplifying ideas that might later be disproven, a fear of being associated with speculation that could be embarrassing if it turns out to be baseless. These fears are understandable, but they're also corrosive to the scientific process. Science advances by being wrong publicly, by proposing hypotheses that get tested and sometimes refuted, by following leads that sometimes end in dead ends. If we only pursue questions that we're confident will yield comfortable answers, we're not doing science, we're performing it for an audience that values certainty over curiosity. And that performance might protect institutional reputations in the short term, but it erodes public trust in the long term, because people can sense when they're being managed rather than informed. Imagine if this situation had been handled differently. Imagine if, when Loeb sent his report to JPL, Nokia had responded publicly, saying something like, "Dr. Loeb has raised interesting questions about 3IATLAS's trajectory and the March 2026 encounter. We've reviewed his analysis and, while we don't currently have evidence to support the hypothesis of intentional targeting, we agree that the encounter is statistically unusual and warrants close observation. We're revising our acceleration model based on updated compositional assumptions, but we acknowledge that observational data remains somewhat ambiguous, and we encourage the community to continue monitoring this object closely." That kind of response would have done several things. It would have acknowledged Loeb's work respectfully. It would have explained the model change transparently. It would have admitted uncertainty where uncertainty exists, and it would have invited continued engagement rather than shutting down conversation. That response would have strengthened trust in the process, even if the underlying scientific disagreement remained unresolved. Instead, what we got was silence, and silence invites suspicion. When institutions don't explain themselves, people fill the void with speculation. Some of that speculation is reasonable, some of it is not, but all of it is a direct consequence of opacity. And in an era where public trust in scientific institutions is already fragile, where misinformation spreads easily, and where skepticism of authority is high, choosing opacity over transparency is not just a procedural failure, it's a strategic failure. It hands ammunition to those who want to claim that science is dogmatic, that institutions are hiding things, that independent voices are being suppressed. And the frustrating thing is, in this case, there's just enough truth to those claims to make them resonate. Let's also talk about the role of independent scientists in this ecosystem. Loeb is not an outsider, he's as credentialed as they come, but he's operating outside the institutional structure that manages 3IATLAS's data, and that gives him both freedom and vulnerability. He's free to ask questions that might make institutions uncomfortable, free to publish findings without needing institutional approval, free to engage with the public directly. But he's also vulnerable to being dismissed as a maverick, to having his work ignored or minimized, to being characterized as someone who's chasing attention rather than truth. This dynamic is important because it shows how the structure of science can create in-groups and out-groups, where those inside the institutional walls control the narrative and the data, and those outside can question but not access or change. That's not inherently wrong, but it requires that the institutions holding that power use it responsibly, transparently, and with accountability. And by that standard, the handling of 3IATLAS has been inadequate. Here's why this matters to you, even if you're not an astrophysicist, even if you never look through a telescope. The way we handle anomalies, the way we respond to questions that challenge consensus, the way institutions balance caution against curiosity, these things shape what we discover and what we miss. If the default response to anomalies is to smooth them over, to fit them into existing frameworks even when the fit is poor, to avoid the questions that might lead somewhere uncomfortable, then we guarantee that we'll miss things that matter. We guarantee that the next great discovery, the next paradigm shift, the next moment where observation forces us to revise our understanding will be delayed or lost because we chose comfort over courage. And if that next great discovery involves something as profound as confirming that we are not alone, that intelligence exists beyond Earth, that technology from another civilization has entered our solar system, then the cost of our institutional caution is not just scientific, it's civilizational. I'm not calling for reckless speculation. I'm calling for proportional investigation. I'm calling for transparency in decision-making. I'm calling for institutions to engage with legitimate questions rather than retreat from them. And I'm calling for all of us as people who care about understanding the universe to demand that standard. You don't need expertise to demand transparency. You don't need a PhD to expect that when data changes, the reasons are explained. You don't need to be a scientist to insist that anomalies be investigated rigorously rather than minimized quietly. These are not technical demands. These are ethical demands, grounded in the principle that the pursuit of truth requires honesty about what we know, what we don't know, and what we're uncertain about. And when those demands are not met, we have both the right and the responsibility to ask why, loudly and persistently, until we get answers that are worthy of the questions. March 2026 is not far away. It's close enough that we can start thinking concretely about what observation will look like, what data we'll be able to gather, and what outcomes are possible. This is the moment when the theoretical becomes empirical, when the models meet reality, and when the questions we've been asking will begin to receive answers whether we're ready for them or not. The encounter with Jupiter is not optional, it's going to happen. 3IATLAS is on that trajectory, Jupiter's gravity is waiting, and the universe doesn't pause for us to decide whether we're prepared to observe something that challenges our expectations. So the question is not whether the encounter will happen, but whether we'll watch it with the rigor, the transparency, and the intellectual courage it deserves. What exactly will happen during this encounter? 3IATLAS will pass within Jupiter's Hill radius, entering the gravitational sphere of influence where Jupiter's pull becomes dominant. The exact closest approach distance depends on which model you're using. But even the revised shallow model places the object within a region where gravitational dynamics become complex. As it approaches, Jupiter's gravity will begin to alter 3IATLAS's velocity and trajectory. If the object is entirely passive, These alterations will be predictable, calculable, and they'll follow the equations of orbital mechanics that have been tested and verified countless times. The object will swing past Jupiter, experience a gravitational slingshot effect that changes its outbound trajectory slightly, and then it will continue out of the solar system, never to return. That's the baseline expectation. But what if the object deviates from that baseline? What if, as it approaches Jupiter, it exhibits course corrections that can't be explained by gravity alone? What if its velocity changes in ways inconsistent with passive dynamics? What if instruments detect energy signatures, radiation patterns, or other phenomena that don't fit a natural cometary profile? These are the outcomes that would demand we revisit every assumption. And the key is that these deviations, if they occur, will be measurable. This isn't about interpretation or ambiguous data. Trajectory deviations from gravitational predictions are binary. They either happen or they don't. And if they happen, the magnitude and direction of those deviations will tell us a tremendous amount about what might be causing them. We have observational assets positioned to gather data during this encounter, though whether they'll all be deployed effectively depends on decisions that are being made now, in 2024 and 2025, about priorities and resources. NASA's Juno spacecraft is currently orbiting Jupiter, and while its primary mission focuses on studying Jupiter itself, it has instruments that could potentially detect anomalies associated with a passing object. Its magnetometer could detect unusual magnetic fields. Its radiation monitors could pick up unexpected emissions. Its cameras, if pointed in the right direction at the right time, could capture images. The European Space Agency's JUICE mission, depending on its position in March 2026, might also have observational opportunities, though coordinating observations between agencies requires planning and communication that isn't always seamless. Ground-based observatories will certainly be watching. Telescopes around the world will be able to track 3IATLAS as it approaches and recedes from Jupiter, measuring brightness, position, and velocity. If the object is bright enough, and if observing time is allocated appropriately, we could get high-resolution spectroscopy that might finally give us definitive compositional data. We could measure rotation rates, look for changes in brightness that indicate active outgassing or other processes, and track the trajectory with precision that allows us to test the models in real time. Space-based observatories like Hubble, if they're allocated time for this observation, could provide additional high-quality data free from atmospheric distortion. But all of this depends on recognition that the March 2026 encounter is significant enough to warrant those resources, and that recognition, in turn, depends on breaking through the institutional reluctance to treat 3IATLAS as more than just another comet. Let's talk about the possible outcomes and what they would mean. Outcome 1. 3IATLAS passes through Jupiter's vicinity exactly as the updated model predicts, exhibiting no deviations, no anomalies, no behavior that can't be explained by passive gravitational dynamics and standard outgassing. In this case, the skeptics would be vindicated. The concerns about targeting, about artificial propulsion, about the statistical improbability of the trajectory would all be explained as natural variation within the range of what comets can do. The story would quiet down, the anomalies would be filed away as interesting but ultimately not paradigm shifting, and we'd move on. That's a possible outcome, and if that's what happens, we should accept it. Outcome 2. 3IATLAS exhibits minor deviations from prediction, small trajectory adjustments or velocity changes that are noticeable, but still potentially explainable by more complex outgassing models or gravitational perturbations we didn't fully account for. This outcome would keep the debate alive. It wouldn't definitively prove anything, but it would provide new data that could either strengthen the natural explanation with better models, or provide evidence that something more is happening. It would require continued observation and analysis, and it would mean that March 2026 is not the end of the story, but a chapter in a longer investigation. Outcome 3. 3IATLAS exhibits significant deviations that cannot be explained by natural processes. Course corrections that are directionally inconsistent with outgassing. Velocity changes that require energy input beyond what passive sublimation can provide. Observable phenomena, heat signatures, radiation, light patterns that don't fit a cometary profile. This outcome would be historic. It would demand a fundamental reassessment of what 3IATLAS is, where it came from, and what its presence in our solar system means. It would move the question from "could this be artificial?" to "how do we confirm this is artificial?" and what do we do with that information? And it would require that the scientific community, the institutions and the public grapple with implications that are as profound as any we've ever faced. The reality is, we don't know which outcome we're heading toward. And that uncertainty is exactly why March 2026 matters so much. It's a moment where nature will provide an answer, where observation will cut through the debate and give us data that moves us forward, but only if we're watching, only if we're prepared, only if the institutions that control the observational resources treat this encounter with the seriousness it potentially deserves. And that's where transparency becomes critical again. We need to know that Juno will be tasked, if possible, to observe. We need to know that ground-based telescope time is being allocated. We need to know that the data gathered will be made public promptly and completely, so that the scientific community and the public can evaluate it together. We need to know that if anomalies are observed, they'll be reported honestly, not minimized or explained away in press releases that smooth over the discomfort. March 2026 is also a deadline that creates urgency for this conversation. We're not talking about some distant abstract future. We're talking about a date that's measurable in months, a moment that's approaching whether we're ready or not. And that urgency means that the decisions being made now about how to observe this encounter, about what resources to deploy, about what level of transparency to commit to, are decisions that will shape what we learn. If those decisions are made with caution and institutional risk aversion as the primary concerns, we risk under-observing a potentially historic event. But if those decisions are made with scientific courage, with recognition that anomalies deserve investigation rather than dismissal, then we maximize the chance that if there is something to discover, we discover it. The universe is offering us a moment of clarity. The question is whether we'll take it. So here's where we are. NASA quietly changed the acceleration model for 3IATLAS without public explanation. The new model fits the observational data less well than the old model. The change happened days after a Harvard astrophysicist raised concerns about the statistical improbability of the object's trajectory toward Jupiter's Hill radius. That trajectory will bring 3IATLAS into a gravitational encounter in March 2026 that represents a moment of observational truth. Either the object behaves as a natural comet should, or it doesn't. And if it doesn't, the implications are profound enough that our preparation for that moment, our commitment to transparent observation, and our willingness to follow the data wherever it leads will define this moment in scientific history. What have we learned today? We've learned that institutional science, for all its strengths, is not immune to failures of transparency and accountability. We've learned that models can be revised for reasons that aren't purely observational, and that those revisions can reshape narratives in subtle but significant ways. We've learned that independent scientists asking uncomfortable questions can be met with silence rather than engagement, and that silence creates voids that erode trust. We've learned that anomalies are often smoothed over rather than investigated, and that this smoothing serves institutional comfort more than scientific progress. And we've learned that an interstellar object exhibiting unusual behavior is heading toward a gravitational encounter that could either confirm our existing understanding or challenge it in ways we're not yet prepared to acknowledge. Your attention to this matters more than you might think. When people pay attention, when questions are asked publicly, when engagement is high and scrutiny is persistent, institutions respond differently than when they believe they can operate in obscurity. The fact that you're watching this video, that you've stayed with me through this detailed analysis, that you're willing to think critically about how science is conducted and what transparency requires, that attention is itself a form of accountability. It signals that there is a community of people who care about these questions, who won't accept silence as an answer, and who expect that the pursuit of truth will be conducted with honesty and openness. That community matters. You matter. So here's what I'm asking you to do. First, stay informed. Follow developments around 3IATLAS as we move toward March 2026. Watch for announcements about observational campaigns, about data releases, about whether the institutions with the resources to study this encounter are deploying those resources appropriately. If you see opacity, call it out. If you see transparency, acknowledge it. Reward the behavior we want to see more of, and challenge the behavior that undermines trust. Second, share this story. Talk about it with people who care about science, about space, about the bigger questions of whether we're alone. The more people who understand what's at stake, the harder it becomes for the story to be managed quietly. Third, Support independent voices in science. Loeb is not the only scientist willing to ask uncomfortable questions, but scientists who do so often face professional risk. Support them with attention, with engagement, with amplification of their work. Make it clear that intellectual courage is valued, not punished. And finally, keep questioning. Not cynically, not with the assumption that institutions are always wrong, but with the healthy skepticism that science itself demands. When data changes, ask why. When models are revised, ask for the justification. When silence is the response to legitimate inquiry, ask again, louder. The pursuit of truth requires that we treat truth as more important than comfort, more important than institutional reputation, more important than the fear of being wrong in public, and the only way to ensure that standard is upheld is to demand it, consistently and vocally, from everyone involved in the process. March 2026 is coming. We will watch together. We will see what 3IATLAS does as it passes through Jupiter's gravitational realm. We will evaluate the data. We will listen to the scientists who interpret it, and we will hold everyone involved accountable to the principle that observation matters more than narrative. If you want to be part of that moment, if you want to follow this story to its conclusion, subscribe to this channel. Hit the notification bell so you don't miss updates. Comment below with your thoughts, your questions, your own insights into what we've discussed today. Let's build a community of people who understand that the most important discoveries often come from paying attention to what others want to ignore. Thank you for being here. Thank you for caring enough to spend this time understanding not just what happened, but why it matters. Thank you for being the kind of person who values truth over comfort, who asks questions instead of accepting silence, who understands that the universe is vast and full of mysteries, and that our job is not to explain those mysteries away but to meet them with curiosity and courage. This story is not over. It's just beginning. And what happens next depends in part on whether we're watching, whether we're demanding transparency, and whether we're willing to follow the data even when it leads somewhere we didn't expect. Stay vigilant, stay curious. And let's see what March 2026 has to teach us, because whatever the answer is, it's an answer worth knowing.